Good morning to everyone. Today's topic is differential calculus. Subtopic is Taylor's theorem for a function of two variables. The statement of Taylor's theorem for a function of two variables is as follows. If f of x, y and its partial derivatives up to nth order are continuous in any neighborhood of a point a, b. That means, observe, f of x, y is a given function. That means, the function f is in terms of x and y. For this function, we can get first order, second order, continuously third order, fourth order, partial derivatives depending on the function f. Observe, the first order partial derivatives are dou f by dou x, dou f by dou y. Second order partial derivatives are dou square f by dou x square, dou square f by dou y square, dou square f by dou x dou y. Like this, we can get third order, fourth order and continuously nth order. All these partial derivatives and the function f is continuous in the neighborhood of a point a, b. Here you can observe this is the point a, b. For this point, this is neighborhood. Neighborhood means it is an open interval. So, this point lies within the neighborhood. And if a plus h, b plus k be any point in this neighborhood, observe, this is one more point lies in this neighborhood only. Here the point coordinates are a plus h, b plus k. Then in this situation there exists a number theta with 0 less than theta less than 1 such that f of a plus h, b plus k is equal to f of a, b. That means the value of the function at a, b. How we are going to get this means by replacing x with a, y with b, plus 1 by 1 factorial h into dou by dou x plus k into dou by dou y of f of a, b, plus 1 by 2 factorial into h dou by dou x plus k dou by dou y whole square f of a, b. Here you observe this term and this term. Here we have 1 factorial and power is 1. Here we have 2 factorial and power is 2. Remaining base term and f of a, b is same, plus 1 by n minus 1 factorial h into dou by dou x plus k into dou by dou y power n minus 1 f of a, b. Here also you can observe, here we have n minus 1 factorial, the power is n minus 1. So, first term, second term, third term, next term is fourth term, like this. This is nth term, plus 1 by n factorial h dou by dou x plus k dou by dou y power n f of a plus theta h, b plus theta k. Here also n factorial we have, power is n. This is n plus 1th term of f of a plus h, b plus k. So, again observe, here the simplification of all these terms we are going to write. Observe, the value of f at a plus h, b plus k is f of a, b. So, we are going to write first term as it is, plus 1 by 1 factorial h dou f by dou x, that is fx, dou f by dou y, that is fy, plus 1 by 2 factorial. Here we are going to use the formula a plus b whole square. So a square plus b square plus 2ab. That's why we are going to get h square dou square by dou x square plus k square dou square by dou y square plus 2hk dou by dou x dou y f of a comma b. So we can rewrite these terms as h square dou x square as fxxx, that is second order partial derivatives of f, plus k square dou square by dou y square of f is fyy, that is second order partial derivatives of f with respect to y, plus 2hk dou f of dou by dou x dou y of f is fxy. So the simplification of this step is this one. So instead of writing this term, we are going to write this step. Observe, here we are writing the simplification of this term, plus dotted lines as it is, plus. So here we are including these two terms in these dotted lines only. We denote Rn. Rn is equal to 1 by n factorial h dou by dou x plus k dou by dou y whole power n f of a plus theta h plus theta h comma b plus theta k. That means this n plus 1th term is called Rn. Observe, here also they mention the same thing. This is the remainder after nth term, because this is the nth term. This is after the nth term means this one only. This value is called Rn. Let a plus h equal to x. From this equation we can get h equal to x minus a. Again b plus k equal to y. From this we can get k equal to y minus b. So now we have the values of h and k. The value of h is x minus a. The value of k is y minus b. Now we are going to substitute these values here. Then we are going to get f of x comma y. Observe, a plus h is replaced with x, b plus k is replaced with y. F of a comma b we are writing as it is, 1 by 1 factorial also as it is. Instead of h we are going to write x minus a. Fx plus, instead of k we are going to write y minus b. Fy as it is, plus 1 by 2 factorial h square here we have. So h square is replaced with x minus a whole square. Fxx as it is, 2 into h value is x minus a, k value is y minus b. Observe here, fxy as it is, plus k square. K square is y minus b whole square. Next into fyy. Here we have fyy. That's why we write fyy. So here we have the equation in terms of h and k. Whenever we know the values of h and k, we are going to replace those values. Then we are going to get this expression. Once again, f of x comma y is equal to f of a comma b plus 1 by 1 factorial x minus a into fx plus y minus b fy plus 1 by 2 factorial x minus a whole square fxx plus 2 into x minus a y minus b fxy plus y minus b whole square fyy. Next, we are going to move to Maclaurin's expansion for f of x comma y. Already we know the difference of Maclaurin's expansion and Taylor's theorem. In Maclaurin's expansion, we are going to consider a equal to 0, b equal to 0. That is, if a equal to 0, b equal to 0, then the expansion of f of x comma y around the origin is called Taylor's series about the origin, or Maclaurin series for f of x comma y. Maclaurin series for f of x comma y and is of the form. So, here we have expression in terms of a and b. Now we are taking a equal to 0, b equal to 0. Then we are going to get, instead of this term, f of 0 comma 0. Here also, in this expression, x minus a, wherever we are getting, those terms are replaced with x minus 0. X minus 0 is nothing but x. Similarly, y minus b is replaced with y minus 0. Y minus 0 means y only, because we are taking a equal to 0, b equal to 0. This is the expression after replacing a value and b value. This is called Maclaurin's series for f of x comma y, or Taylor's series about the origin. The remainder after nth terms is, in this case, will be Rn equal to 1 by n factorial x dou by dou x plus y dou by dou y whole power n f of theta x comma theta y. Here also we are taking a0 and b0, and this value tends to 0 as n tends to infinity. Further, if the Taylor series of f of x comma y is approximated to some terms up to a particular degree by resulting expression of f of x comma y is called as the Taylor's polynomial. So, if in the question, if they ask expand the given function up to 4th degree, then the answer is called Taylor's polynomial. If they given up to particular degree, then Taylor's series becomes Taylor's polynomial. So, observe the first question. Obtain the Taylor's expansion of f of x comma y equal to x square y plus 3y minus 4 in powers of x minus 1 and y plus 2. Observe the given function is in terms of x and y. Once again, obtain the Taylor's expansion of f in terms of x comma y. It is x square y plus 3y minus 4 in powers of x minus 1 and y plus 2. Now we need the values of a and b. For this, we are going to compare x minus 1 with x minus a. Then we can easily find out a equal to 1. To get the value of b, we are going to compare y plus 2 with y minus b. This y plus 2 can be written as y minus of minus 2. So, the b value is minus 2. Now we have a value and b value. How we are going to get a value, b value means, here we have x minus 1 and y plus 2. Compare x minus 1 with x minus a, y plus 2 with y minus b. Then you are going to get a and b values. Okay. Next, solution. F of x comma y equal to x square y plus 3y minus 4. From the given data, a is 1, b is minus 2. We already known That's why we can write here as easily. Now we are going to find out f, that means the value of the function at 1 comma minus 2. For this we are going to substitute x equal to 1, y equal to minus 2 in the given function. Observe 1 square minus 2 plus 3 into y value minus 4. After simplification, we are going to get minus 12. Observe 1 square is 1, 1 into minus 2 is minus 2, 3 into minus 2 is minus 6, minus 4 as it is. So, the simplification of this is minus 12. So, the value of f of 1 comma minus 2 is minus 12. Now, we are going to find out partial derivatives of f. So, first one is partial derivative of f with respect to x. So, all of you know, whenever we are doing partial differentiation with respect to x, we are keeping y as constant. So, this is the given function. Now, I am going to do partial differentiation of this function with respect to x. We denote fx. Fx means partial differentiation of f with respect to x. While doing this partial differentiation, we are treating y as constant. So, keep this y as constant. X square differentiation is 2x. So, observe y constant. So, 3 into y is again constant. Minus 4 is constant. That means this total function is constant. So, the differentiation of constant is 0. So, the partial derivative of f with respect to x is 2xy. Now, we are going to find out the value of fx at 1 comma minus 2. Substitute x with 1, y with minus 1. So, 2 into 1 into minus 2. So, 2 2s are 4. Here we have minus sign. That's why we are going to get minus 4. Next, we are going to find out fy. That means partial differentiation of f with respect to y. While doing this partial differentiation, we are keeping x as constant. Whenever x is constant, x square is also constant. So, keep x square as constant. Partial differentiation of y with respect to y is 1 plus 3 into 1. Constant differentiation is 0. So, we are going to get x square plus 3. So, this is this one. Okay. Now, the value of fy at 1 comma minus 2. So, replace x with 1. Then we are going to get 1 square plus 3. 1 square plus 3 is 4 itself. Next we are find out second order partial derivatives, that is fxx, fxy, fyy. Fxx, that means we have already fx. We are going to differentiate fx again with respect to x only. Here 2 is constant, y is constant. So 2y into 1, that is 2y. The value of fxx at 1 comma minus 2 is 2 into y value is minus 2. That's why minus 2. 2 into minus 2 is minus 4. Next, we are going to find out fxy. This partial derivative we are going to get by differentiation fx with respect to y. With respect to y means x is constant. So 2x is constant. For y, the differentiation is 1. Finally, the value of fxy is 2x. Now we find out the value of fxy at 1 comma minus 2. So 2 into x value is 1. We are going to write 1 here. 2 1s are 2. Next, we are going to find out fyy. How? Means differentiate fy again with respect to y. While doing partial differentiation with respect to y, we are considering x is constant. Whenever x is constant, x square is constant, 3 already constant. That means this is totally becomes constant. Constant differentiation is 0. Now we have fx, fy, f_x, fxy and fyy. Substitute all the values in the Taylor's series. This is the Taylor's series. F of x comma y equal to f of a comma b plus 1 by 1 factorial x minus a into fx plus y minus b fy plus 1 by 2 factorial into x minus a whole square fxx plus 2 into x minus a into y minus b fxy plus y minus b whole square into fyy plus dash dash. So that means we can write third order partial derivatives here. Next fourth order partial derivatives continuously. So here we are stopping up to second order partial derivatives. So f of x comma y, this is the given function, is equal to f of a comma b, we already know. Substitute 1 by 1 factorial as it is, a is 1, x minus 1, fx value is minus 4, b value is minus 2, minus of minus is plus, that's why y plus 2, fy value is 4 plus 1 by 2 factorial, x minus 1 whole square, fxx value is minus 4, 2 into x minus 1, y plus 2, fxy value is 2 plus y plus 2 whole square, fyy value is 0. Now we substitute all values, that means a value, b value, fx, fy, f_x, fxy, fyy. Now the final Taylor's expansion of given function is minus 12. Here observe minus 4 into x minus 1 plus 4 into y plus 2 because 1 by 1 factorial is 1 itself. Here observe plus 1 by 2 factorial. We know that 2 factorial is 1 by 2 only. 2 factorial means 2 only, 1 is numerator as it is. Here you can observe, here minus 4 is there, here we have 2 is there. So we can take 2 as common, take 2 common, then x minus 1 whole square minus 2 plus 2 times of x minus 1 y plus 2. Here I am not writing this term because 0 into anything is 0. So 2 and 2 get cancelled. Then we are going to get minus 2 into x minus 1 whole square plus 2 into x minus 1 into y plus 2 plus dash dash. This is the Taylor's series of the given function x square y plus 3y minus 4.